welcome to C9 Daily News. I am Carla Marjocaras with today's exclusive news. A book of Ian Stewart, Nature's Number, has been trending all over the world. Many of the readers of this book found the chapter 9 entitled Drops, Dynamics, and Daisies interesting as an ending for the book. Ian Stewart is a British mathematician, a popular science, and a science fiction writer. He is best known for his famous science writings, mainly on mathematical themes. He had published more than 120 books, which includes the trending Nature's Number. If you don't know, Nature's Number is all about seeing nature from a mathematician point of view. For the talk of the town ending chapter of Nature's Number, we are going to feature it and we'll discuss it to you one by one. Nature's Number Chapter 9 engages us to a mathematical world in nature. The thought of the end chapter circulates on the idea how simplicity emerges with complexity. This will enable us to see the world in different perspectives, but would also amaze us on how great our world we live in. Drops, Dynamics, and Daisies is what composes a Chapter 9. Here is a short preview for each.
What you see is just a simple drop of water from the tap. Small and adorable brown rabbit. And a beautiful field of flowers. As you go on in this video, you will able to see how complexity lies to each of them. It will either supplement your knowledge or change what you had once thought it is. And lastly, you will be enlightened to how they interlink to each other.
We'll now move on to our reporters in school for their exclusive report for the worldwide trending book.
For the first headline, today we'll tackle about the shape of water dripping from the tap. According to the book of Nature's Number by Ian Stewart, he believes that this example shows the idea of complexity emerging from simplicity. If we look into the details or the process of how the water drops off the tap, it becomes so complicated that the simplicity is lost. This is actually an everyday phenomenon. Yet, it has shown us about chaos, and now it will teach us something about complexity. In this example, we do not focus on number of drop it takes, but we focus on the shape that it forms as it detaches from the end of the tap. As obvious as it is one look, and we can say that the shape of the water droplet is in the classic form of a teardrop, round at the head and curving away to a sharp tail. What's more fascinating is that it is actually not its true shape, and we believed this illusion for a very long time. With our naked eye, if we look the water dripping from the tap, it may seem like a teardrop shape or a circle one. But in 1990, mathematician namely Howell Peregrine and colleagues at Bristol University photographed the process and discovered that it is far more complicated, but also far more interesting than anybody would ever imagine. The formation of the detached drop begins with the bulging droplet hanging from a surface. At the end of the tap, it develops a waist which narrows, and the lower part of the droplet appears to be heading towards the classic teardrop shape. But instead of pinching off to form a short, sharp tail, the waist lengthens into a long, thin, cylindrical thread with an almost spherical drop hanging from its end. Also, did you know that in early literature contains only one drawing of it? Do you have any ideas who draw it? It was made centuries ago by the physicist Lord Rayleigh. He is an English physical scientist who made fundamental discoveries in the fields of acoustics and optics that are basics to the theory of wave propagation in fluids. Isn't it amazing? Isn't it surprising? Isn't it? The water droplet is very small, yet it has a complicated process of forming. With that, there is really complexity within simplicity. Francina Blayan reporting. Now, let's call on Vince for the next report.
The next example given by Stewart was a simplified version of a game cited from the work of Jackie McLeod David Rand and Howard Wilson of Warwick University in 1994. Through the use of this example, he further emphasized the concept of simplicity amidst complexity and vice versa through the use of a computer game portraying the dynamics of a rabbit population. Second example deals with a game simulating an artificial ecology of which the events also matches as to what happens in a real ecology, albeit portrayed in a different manner, which is through a computer board game with a set of rules and various variables. The main idea is quite similar to that of a drop of water falling from a tap. The more you focus your attention to the smaller details, the complicated it appears to be. But if you look at it in a general perspective, what happens is only the simple occurrence of a water dropping from a tap. But in this particular example, what happens in a general perspective is the change in the rabbit's population. Similarly, if you look at this video, at one glance, we will be able to recognize what this video is all about. On the other hand, if we zoom the video too much and focus it only on a small particular section, what we will see will be but a chaotic and complicated mess of a thing which is entirely incomprehensible, resulting to a complicated and blurry scenario. As such, we can conclude that indeed, in every phenomenon of the world, there exists either simplicity or complexity, all of which is entirely dependent on our own perception. This is Vince Christian Simbrano reporting.
Fibonacci was found. Fibonacci was found on the number of petals of the flowers? Wait, are you sure about this script? Oh, okay. Back to regular programming. For our last headline, we'll study about the nature, specifically the flowers, having the presence of the Fibonacci sequence in them. Yes, it is confirmed that Fibonacci sequence was found on the number of petals on the flowers. This is an example of a mathematical regularity of nature that emerges from complexity rather than having a built-in with the rules. The number of petals of every flower display mathematical regularities and form the beginning of so-called Fibonacci sequence or series.
However, it doesn't only end there. If you look close to each flowers, you can see more of the Fibonacci sequence. Let's take a look at this giant sunflower. The florets are arranged in two intersecting families of spirals, one winding clockwise, the other counterclockwise. The clockwise spirals are counted 34, and the number of counterclockwise spirals is 55. Both are Fibonacci numbers, occurring consecutively in the series. It may depend on the species of flower sometimes, nevertheless, often get 34 and 55, or 55 and 89, or even 89 and 144. If this sequence appears in various natural creations, are they all coincidental? Is the science genetics pattern? Or it has to be the mathematics natural pattern? There were people who studied this sequence of patterns, and today we're lucky to have our guest that would explain us the secret behind the Fibonacci numbers located in the flowers. We have online Mr. Stéphane Douady and Mr. Yves Quadre, the two French mathematical physicists who came up with the theory of the dynamics of plant growth.
Good day to each and everyone. It is our pleasure to be featured here.
Mr. Duwadi and Mr. Quader. Upon delving this theory of the dynamics of plant growth, what have you discovered?
Let's start from the very basic idea. Try to look at the tip of a growing plant. At the center of it, there is a circular region of a tissue called apex. Around it, we have a tiny lumps called primordia. In each primordium, it migrates away from the apex, and then the apex grows away from the lump, and eventually develops into a leaf, petal, or the like. And this explains why you see a spiral shapes and the Fibonacci numbers in the primordia. What then you found is a generative spiral of successive primordia. Now imagine drawing lines from the center of successive primordia to the center of the apex, and measure the angle between them. The successive angles are more likely equal, and thus the common value is called divergence angle. Divergence angle is usually very close to 137.5 degrees. This was emphasized by Auguste Verviers and Louis Verviers. The angle between successive primordia is the golden angle of 360 times 1 minus phi is equals to 137.5 degrees. Because of the way the points align, our eyes perceive two spirals, one winding clockwise and the other counterclockwise. And due to the relation of the golden ratio and the Fibonacci numbers, the number of the spirals are consecutive Fibonacci numbers. Then we had conducted an experiment, not with plants. Instead, using a circular dish full of silicone oil placed in a vertical magnetic field. When the team dropped the oil slowly, the droplets moved directly away from each other. But when we increased the speed, two older droplets would repel the new droplets simultaneously. So instead of simply repelling each other, the droplet would move in a third direction, at the golden angle from the line connecting the drop's landing point with the previous droplet, thus giving a sunflower seed a pattern of interlaced spirals. In addition to this, we had carried out computer calculations that had similar results to the first experiment. By doing both, we had found a divergence angle depends on the interval between drops according to the complicated branching pattern of wiggly curves. After all this, we cannot state that botany is ideal and perfectly mathematical. So maybe what the genes do is to affect the timing of the appearance of the primordia. But plants do not need their genes to tell them how to arrange their primordia. That is done by the dynamics. It is just a matter of physics and genetics, and you need both to understand what is happening.
That quite answer my question. In the end of this, it is still the nature's secret and how to adapt to its own surrounding. Thank you for this complex yet amusing discussion and for imparting your knowledge to us, Mr. Kawader and Mr. Dawadi. We have learned something today, and I hope that the viewers have gained some understanding too. That's it for our last headline for today. It is indeed amazing how nature works in mysterious yet incredible way. Don't you think? Hope you learned a lot. This is Jeliza Hopiswenya reporting.
The book ends by drawing a kind of philosophical conclusion. Chaos theory has all sorts of implication, but the one Stewart closes on is this. The world is not chaotic. If anything, it is boringly predictable. And at the level of basic physics and math, the laws which seems to underpin it are also schematic and simple. And yet, what we are only really beginning to appreciate is how complicated things are in the middle.
It is as if nature can only get from simple laws to fairly simple outcomes via almost incomprehensibly complex processes. Therefore, chaos teaches us that system obeying simple rules can behave in surprisingly complicated ways. Three cases being studied serves as an eye-opener to all of us. It made us realize that our world is just simple, but we are divulging deeper for the message buried within that turn simplicity to complexity.
It is so fascinating to know that through mathematics, we are able to decipher these puzzles through the clues left by nature, which develops our understanding. To end this review, we will lay down what we believe is the significance of this in real life situations. In our opinion, the idea complexity derived from simplicity and vice versa is similarly applicable to real life scenarios. This is especially true when we are answering problems in different situations.
Complexity arises the moment the brain overthinks the possible scenarios and consequences that may happen as a result of certain action or decision. On the other hand, simplicity arises when we don't think too much about the problems at hand and just do what we can for the meantime. So, in a sense, both complexity and simplicity arise depending on how we approach or view our problems in life, which is greatly similar to the three specific examples that I and Stewards have presented.